Hello, in this video we're going to be talking about inverse functions, which are functions that undo each other, and we're also going to be talking about their domain and their range. Only a particular type of function has an inverse. It needs to be a one-to-one function. A one-to-one function is a special type of function where it passes both the vertical and the horizontal line test. If we look at both of these functions, we can tell that both of them pass the vertical line test. However, only one of them passes the horizontal line test. So if we pass a horizontal line across it, this cube root function is a one-to-one function because as this horizontal line moves up, it's only ever touching it once. However, an absolute value graph does not pass the horizontal line test because there's lots of points on a absolute value graph where that output shows up more than once. So they're both functions, but cubic is a one-to-one function because it passes the horizontal line test, and absolute value is still a function, it's just not a one-to-one function. If we think about some other graphs that are not one-to-one functions, step function is definitely not a one-to-one function. It is a good function, passes the vertical line test, but it's all horizontal lines. So if it's all horizontal lines, then it's definitely not passing that horizontal line test. So step is not one of our one-to-one functions. Now, an important function that we do a lot is quadratics. In quadratics, great functions. They pass the vertical line test. That is a quadratic that's just being shifted up one, but quadratics do not pass that horizontal line test. So in terms of functions, a quadratic doesn't have inverse because it's not a one-to-one function. Now, we do know that we still find the square root and squares undo each other. So in that sense, there is sort of an inverse, but if we think about like solving those types of equations, we get extraneous. And it's the reason we get those extraneous is because of this problem of quadratics not being proper one-to-one functions. If they were proper one-to-one functions, we wouldn't have to deal with extraneous solutions when we solve square roots or quadratics. So inverse functions are one-to-one functions that undo each other. And what I mean by undoing each other is that if we compose those functions with each other, both times we get just an x. So first we have to check is what is f of g of x? What happens when we put f into g of x? So or g or the way around, whatever. We got to do both, okay? So we're going to put this where that x is. So f of 2 plus 2x plus 4. So when we put that in, we get 1/2 times 2, that is x, and half of 4, that's 2. 2 minus 2, that is 0, so we get just a plain x. So it works on that direction, but it has to work on the other direction too. When we do g of x, we're going to take g of x and put f of x into there. So g of 1/2 x minus 2. So we want to replace this x right here with a 1/2 x minus 2. When we do that, 2 times our 1/2 will get us 1x. 2 times 2 will get us 4. And then that negative 4 plus 4, that is going to be 0. So we get just an x. That means that f of x and g of x are inverse functions because they undo each other. When we compose them, they both produce x. In this example, we want to verify if these two functions are inverses of each other. In order for them to be an inverse, we have to compose those two functions, and both times we get just an x. So if we start with f of g of x, that means we want to put 1 over x where that x is in f of x. So we want to do the square root of 1 over x. In order to simplify this down, I can square at the top and square at the bottom. So I get the square root of 1 over the square root of x. I could square root the 1 on the top, so that's just going to be a 1 over the square root of x. And I could rationalize that denominator to get the square root out of the denominator, but I think that's about enough. I'm not going to get to just x. Let's check what's going on with g of f of x. So what happens when we put this square root into the denominator of g of x? So replacing the f the x with an f of x and putting a square root of x in that denominator, well, hey, that's just a 1 over square root of x. That's the same as what we just got. So even though we got the same thing both times, we got a 1 over square root of x, 1 over square root of x, that does not mean that these two are inverses of each other. They need to compose so we just get x. So even though we got the same thing, that does not mean they are inverse functions. So far, we've been talking about what an inverse is and verifying it, but how do we actually find an inverse? In order to find the inverse, you swap the location of x and y. That actually creates the inverse, but then we make it look pretty. That's the solve for y step. In order to figure out what the domain and range of that is, you take, just like you swapped x and y, you're going to swap domain and range for the inverse. So the domain of the original is the range of the inverse. Once you're done, give yourself some ice cream. So I want to figure out this thing's inverse as well as its domain and range. This is a linear function. It's just been stretched and slid a little bit. So its domain and range is just all real numbers, all real numbers. Then what we need to do in order to create that inverse is we want to swap the location of x and y. Remember that f of x is just a fancy y, so we're going to replace that f of x with a y, and then swap their location. So then we get an x equals 7y minus 3. In order to make it look nice, that is the inverse in green there. In order to make it nice, we solve for y. So we add that 3 to the other side, we divide by both sides by 7, and so that is our inverse. And we made it look nicer. We had it in green. I just made it look nicer here in yellow. In order to mark it as our inverse of f of x, we use this notation of f with a little -1 exponent that represents inverse. It's not a -1 exponent. It represents the idea of inverse for function notation. And so this is our inverse. In order to find the domain and range, we swap these two, but it doesn't really look like much changed. We just take this thing's domain, which is infinity, negative infinity, infinity, that goes here, and that goes there. But it doesn't look like anything swapped because the domain and range are the same. In this example, I want to figure out what the inverse of g of x is, as well as the domain and range of both functions. G of x has a domain of 0 to infinity for both domain and range, but because of that -1, that is changing our domain to be 1 to infinity. That slide to the right one is increasing our range, our domain values by 1 each. So to find the inverse of g, what I want to do is swap the locations of x and y. G of x is just a fancy way to write y. And now I've got that y, that x. I'm going to swap their locations. X and y swap places. So we get x equals the square root of y minus 7. This is our inverse. We found it already. But I want to make it look nice by getting y by itself. So first thing I'm going to do is I'm going to square both sides so I can get rid of that square root, and then get rid of this -1 that's with the y by adding it to the other side. So that is our nicer looking inverse. We already had the inverse. I'm just trying to make it look nice. Once we get that y, we want to write that as our inverse. So we do that with a little -1 exponent. In function notation, that -1 exponent means inverse. This is g inverse of x is x squared plus 1. In order to mark the domain for g inverse of x, I wouldn't just look at what a quadratic is, because this thing's domain and range needs to be the swapped version of what g of x is. Normally, a quadratic, its domain is all real numbers. Not this one, because it's the inverse of g. So its domain is the range of g of x, so 0 to infinity. I also don't try to think about what is the range of a quadratic, because its range is the domain of the g of x. I need to use the domain and range from the original function to figure out what the domain and range of the inverse is. And it's as simple as swapping them around. That is it for our video on inverse functions. Remember that inverse functions are functions that undo each other. They have to be one-to-one by passing both the vertical and horizontal line test. Vertical to make them a function, horizontal to make them one-to-one. Make sure that when you compose them, they both produce x. In order to find that inverse function, you swap that x and y, solve for y, and then use the original's range as the domain of the new function, and the original's domain is the range of our inverse. Thanks so much for watching and taking good notes, and bye-bye.